Hey everybody, welcome back to another awesome Master Science channel video. Today we'll be talking about kinetics. Kinetics is a study of the speed of a reaction and all the factors that affect it.
Oh, let's just make some snacks before we start. How about popcorn? So, why does my popcorn pop?
Each kernel contains approximately 20% water enclosed in its hard shell. On heating the kernels, heat energy is transferred from the pan, giving the water molecules more energy. This increase in energy overcomes intermolecular force energy in water, this is hydrogen. So the molecules have a higher energy state and are free to move and become gaseous, expanding, increasing the pressure and causing kernels to pop. That happens due to collisions of the molecules with sufficient amount of kinetic energy. Collisions obey the kinetic theory of gases, of which has 5 assumptions. All molecules are travelling through space in a straight line. All molecules are rigid spheres. The reactions concerned have only 2 molecular steps. The molecules need to collide. And lastly, only collisions with correct energy will result in a reaction.
The amount of correct energy is called energy of activation. A catalyst speeds up a reaction by lowering the activation energy by providing an alternative pathway. Today we'll be doing an experiment in which all reactants are in solution. Although this is a different state of matter, we can still apply the principles of kinetic theory of gases. The speed of all reactions depends on the rate of successful collisions. The collision theory of gases gives the rate constant for bimolecular gas phase reactions. It is equal to the rate of successful collisions.
The dependence of the rate of reaction on the concentration of the reactants can often be expressed as direct proportionality, in which the concentrations may be raised to a 0th, 1st or 2nd power. So, if the reactant is 0 order, its concentration does not have any effect on the reaction rate. Whereas a first order reactant's concentration will affect the rate in direct proportion. And if you have a second order reaction, the reactants will influence the rate exponentially. The exponent is known as the order of the reaction with respect to that substance. In the reaction above, the overall order of the reaction is given by the following formula. Order equals m plus n. This experiment will figure out the rate of the following reaction. This can also be written as. This will be done using a technique known as quenching, which involves immediately stopping a reaction by removing small portions and adding them to another reagent.
In the first step, we are mixing 2 solutions together. One solution contains potassium persulfate and the other solution contains potassium iodide. Once these solutions are added together, they make a 1:2 stoichiometry ratio. We use this ratio as we want to form iodine as a product. For the experiment, a catalyst is not needed. The reaction is favourable due to the low activation energy. The reaction is quenched at different time intervals using distilled water. This reacts with the reactants to form potassium hydroxide. You no longer have the reactant available to form more iodine, essentially stopping the reaction. Here we added a few drops of starch indicator. When it reacts with free iodine, it forms a black complex. The reason for this is so that the colour change is more visible when looking for the end point in titration. Sodium thiosulfate reacts with iodine during the retitration to form iodide and turns the solution from black to colourless. In order to find out the iodine concentration, we titrate using a known volume of sodium thiosulfate.
Now that all the data has been gathered, using the concentration of I2, the concentration of persulfate can then be calculated. We can plot graphs of concentration against time to determine whether the reaction was 0, 1st or 2nd order. That will indicate the concentration of I2 and on whether it has any effect on the reaction. There are other factors affecting the rate of reaction as well. They include things such as the orientation of the molecule, the temperature, the presence of a catalyst, and the nature of the reactants themselves, the surface area or the phase. In summary, the kinetic theory of gases has 5 assumptions that describe the interactions between molecules, and these principles apply to chemical reactions, in solution as well. Factors affecting rate of reaction are temperature, the physical state, presence of a catalyst or solvent, and the concentrations of reactants. Also, the rate of reaction is represented by the formula rate equals K, A to the M, B to the M. And lastly, the order of reaction demonstrates how the concentration of reagents influence the rate.